Hello and how are you? Welcome to this tutorial in which you are going to handle the topic cathode rays and cathode ray tube. Basically, it's our topic number 37 accordance to the curriculum, and I shall be your tutor, Dave Joseph Adeli. Before we begin, let's have a quick word of prayer. Father, Lord in heaven, we invite you in this session that you may be able to guide us in each and every activity we're going to undertake. In Jesus' name I pray. Amen. Now, basically, there are specific objectives in which we should be able to achieve by the end of this topic. And the main way to be able to notice this is that by the end of this topic, you as the learner should be able to, 1, describe the production of cathode rays, should be able to state the properties of cathode rays, explain the functioning of cathode rays, oscilloscope, that's a CRO, and a television tube, or simply a TV tube. You should also be able to explain the uses of a cathode ray oscilloscope, and finally solve problems involving cathode ray oscilloscope, that's a CRO. Now in this tutorial, you shall be able to learn or be able to describe the production of cathode rays and also state the properties of cathode rays. The rest shall also be covered in the upcoming tutorials. Basically, what are cathode rays? You may just maybe raise a concern. What are cathode rays, or why do we bring up the term cathode rays? Basically, first of all, I believe the term cathode is quite familiar by noticing that that this term cathode basically comes to us from the topic current electricity. We have covered that, current electricity 1 and current electricity 2, and also in chemistry, if you have been able to come in contact with the topic called electrochemistry. If not, it shall also be covered with time. There's something called cathode. Basically, it has been covered as the negatively charged electrode. So basically, that's what we have. If we have terminals of a particular cell, the cathode is basically the negatively charged electrode. And basically, from our previous topics, that is basically under electrostatics, you're able to see how we can be able to distinguish a cathode and the positively charged electrode. Basically, the cathode attracts cations. That's from the basic law of charges. Cations are positive charges, and the cathode of is a negatively charged electrode, so it attracts positive charges, or simply cations. So the cathode is the source of electrons, or simply an electron donor. So as it is a negatively charged, it discharges or it donates electrons. Notice, when you have a cell, the cathode is negatively charged, and because unlike charges attract each other, the positive charges will attract the negative charges, and because the electrons are the ones that flow, which are the negative charges, they are the ones that shall flow towards the positive terminal. And in the same case, we looked at under electrostatics that the moment electrons, or simply the negative charges, move from the cathode, the cathode becomes more of positive charges, and that it becomes positively charged. And basically, because positive charges are stationary, it's very unlikely to find that positive charges will move. So in the sense that they move, it's attracted by the cathode. But basically, we explained that in electrostatics. Now that drives us to just spark some thought. What about an anode? We have looked at a cathode. What about an anode? Anode is basically, from what we have learned, is that the anode is the positively charged electrode. So the anode attracts electrons because it's positively charged, or simply anions. And cations and anions, how to differentiate them, cathode and anode, we looked at it in the previous tutorials. So the anode is the source of positive charges, or simply an electron acceptor. So it accepts electrons because it's an oppositely charged to cations. Now, what are then cathode rays? We have said the cathode deals with negative charges because it possesses negative charges, and that's what it can give. So what then are cathode rays? It therefore means the cathode rays should have some relationship towards the negative charges, or simply electrons. So with that in mind, we should then have a way of how to think, then how can then electrons be dislodged? Because in this case you're not now speaking about the circuit. We should now have rays and not the electric circuit. So basically cathode rays are simply the electron beam, or simply what we call E-beam. They are streams of electrons observed in discharge tubes. Basically, we're going to look at what are examples of discharge tubes. Now, the question is, how are they emitted then? Because we have now come to give a definition that cathode rays are simply streams of electrons observed in discharge tubes. How are they produced or emitted? Now, you'll notice something as we go on. They are produced through a process known as thermionic emission. Thermionic emission is simply the process of emission of electrons due to heat energy. Now let us just explain thermionic emission. When a metal is heated to very high temperatures, electrons may be emitted from its surface. So basically, if I have a metal surface, for example aluminium, if I heat it up well enough, you'll find that the electrons, because they are the ones that they possess kinetic energy, when they are heated, they will be emitted from the surface, and when they are emitted, they dislodged and they can move anywhere depending with how they are attracted. So basically, that's what the thermionic emission process is all about. Now, from chemistry background, we have been able to notice that electrons are outlined in energy shells. Now, because they are outlined in energy shells, the outermost electrons are more easily lost or are more easily dislodged from the metal surface when they possess enough kinetic energy than the ones that are closer to the nucleus. So when they are heated up, they gain kinetic energy, and I believe from particulate nature of matter, we know that matter is at constant rate of motion. So when they are heated, the motion rapidly continues and increases with the time. And from chemistry background, you know that there are bonds. Those bonds break up, and the moment they break up, the electron now gets dislodged because it has gained enough kinetic energy such that the bonds have been broken, and it is now dislodged from the metal surface. So basically, this is because the electrons gain enough energy to enable them break loose from the force of attraction of the nuclei. We'll be able to explain that. Now, let us look at the thermionic emission now under the environment of a cathode, the cathode ray tube or cathode rays. Now, we shall use this diagram here on the screen to be able to explain that. Here we shall have something. So in this case, we have two circuits. If you notice, there is a first circuit in which we have the AC source, which is the 6 volt here, the AC source, which is 6 volts. This simply means alternating current, so the current is alternating. Here we have a rheostat. We also have a 12 volt DC source here, the direct current, and we have a milliameter here, and then you have an evacuated glass bulb. What does it mean by evacuated glass bulb? Just to spark interest, evacuated glass bulb simply means this is a vacuum. It has been evacuated. Evacuated simply means it is void of something, and it's void of air. Basically, that's what it is. Notice that here we also have a gap. This circuit is not complete, so there's a gap here. We shall also explain why the gap is there. Now let's begin from this first circuit here. We find that the moment this circuit is in place, we don't need a switch here because everything is just intact. There will be no current that will be recorded here at the milliammeter because the circuit is not complete. So there is something that would happen here that has not taken place. So let's come to this circuit that we have the AC source, which has a voltage of 6 volts. We find that the moment this switch is closed, there shall be flow of electrons, and basically it's just flow of current. So as it flows, there's a heater filament here, and we know that there's a heating effect when current flows through material. So as it flows through this material, there's a heating effect that is caused, and that heating effect directly heats up this cathode. And you have said that the moment you heat a particular metal, it emits electrons. Now, it emits electrons. There's a condition that has to be met. We said that it has to gain enough kinetic energy. Now, this depends with something known as work function. Work function is basically the minimum amount of energy that is required to dislodge an electron from the metal surface. This will be basically explained well in photoelectric effect, but I'm just using that idea so that you may be able to understand it more clearly. So the moment this heat filament gains enough heat that can heat up this cathode to dislodge electrons, electrons usually align themselves on this particular surface here. So the moment they align themselves there, because they have dislodged, they are just on the metal surface, this anode attracts the electrons that have been dislodged from the metal surface, because now they are free, they are not bound to anything. So the moment they are dislodged, the anode attracts them up. So streams of electrons move about, and these streams of electrons, or basically the beam of electrons that moves about, is basically what we call cathode rays. So what we are seeing here in the dots moving to the anode is what we call the cathode rays. Now, something else that you'll notice, as they move, the circuit now becomes complete. Why? This is we have the negative charge, the negative terminal, whereby electrons should flow towards the positive terminal, and here the circuit has been made complete. So as they move towards the anode, the moment they reach the anode and move upwards, there shall be a current recorded at the milliampere. This will be able to tell us clearly, or give us proof evidence that there is current flow, or simply cathode rays have been emitted in this particular point. So basically that now gives us a good way of understanding thermionic emission, just with this diagram. And I've also explained much greater of how cathode rays are affected in the cathode ray tube, whereby it is used in this case with as the evacuated glass bulb. But this is just a demo. We are going to get more complex things ahead. Now, just considering the heating filament, we have two ways in which you can heat our heating filament, whereby it's basically heating up the cathode. There are two ways, and basically we can either have them directly heat the cathode, or indirectly heat the cathode. Now, when directly heating up the cathode, this basically entails passing of current through the cathode, or simply the filament, which is in the form of a wire. So basically we have our wire here, flow, and the current will flow. So the heating filament is here, and in the same case the heating filament is still the cathode. So as it heats up, it will just be dislodging electrons. The same thing happens here. So all the connections will be done through that particular cathode, and the same thing also applies here. But now here we are having an indirectly heated cathode. What does this entail? You find that indirect heating is where the cathode is made up of a hollow metal with the heater element inside the cylindrical cathode. So here now we have things quite different. We are going to see how it becomes, where we are stating it as a cylinder. You'll notice it more clearly. Though here we're having a two-dimensional figure, we shall be able to see it more clearly, probably in the following diagrams. So one more thing that should yet be known from the thermionic emission that we stated here, because different metals have different work functions, we now bring about something that can be able to have a common value of what we term as the work function. Now here we are going to introduce something known as metal oxides. Now metal oxides, there are specific metal oxides that we apply on the cathode so that we may have lower work functions on that particular metal, so that it emits the electrons with minimal amount of energy. Examples: you have barium or barium oxide, you have strontium oxide, we also have thorium oxides. but it shall be also explained much more in the later stage. So barium or strontium or thorium, they have lower Wang functions, so that's why they are applied on that particular metal cathode, so that it can minimize the amount of energy stated there. Now, production of cathode rays. Cathode rays are produced in a cathode ray tube, or simply what we call a CRT. They are streams of high energy electrons moving from the cathode to the anode. And if you have this particular diagram, whereby now we have the cathode here in the form of a cylinder, and a heater element is inside that particular cathode, and the cathode is outside, so it indirectly hits the cathode, whereas the heater is inside that cathode. So as it hits, electrons are dislodged, and remember, the cathode is coated with metal oxides, in which those metal oxides reduce the work function. They have a lower function, so the amount of energy that will be used to dislodge the electrons will also be minimal. Now we have things here that have also been introduced. We have an anode, we also have a vacuum fluorescent screen. Now we are basically updating the previous diagram. Now the anode here, now in this case, you will find that it is hollow. Why it's hollow, we shall also explain it in a later stage, where we're going to be looking at the CRO, what we call the cathode ray oscilloscope, which is basically an advancement of a cathode ray tube. So the anode here, basically, if I just give you a hint, the anode simply accelerates and focuses electrons on the fluorescent screen. So that's what we basically have as the anode. Now if you notice from this setup here, because we are not now having two circuits separate as we had earlier, we are now connecting the anode and the cathode to something known as EHT. What is EHT? EHT is basically extra high tension, or simply a high voltage device, or a high voltage source. That's what we term as EHT, extra high tension. So the positive terminal is connected to the anode and the negative terminal to the cathode. So basically there is an electric field that is generated at this point because of the difference in potential difference. So with that difference, the anode attracts the electrons. They are accelerated towards the fluorescent screen, and there we have our cathode rays. I believe you can also see that from there. Now we want to look at properties of cathode rays. Now we are going to use very short clips here and try reasoning them out. Have a piece of pen and paper, and then try just gauging up to see what you can be able to deduce from these particular clips. Now let's play the first one and then try deducing the properties that you see. What do you think? I've noticed a greenish yellow substance that is towards the end of that particular tube. So there's something about the greenish yellow. What about that greenish yellow? I believe you have noted that they cause certain substances to glow, in most cases showing a greenish fluorescence or a glow. So that's one of the properties. So the cathode rays cause certain substances to glow, whereby in most cases they show greenish fluorescence, or they glow. Let's try the second one. So the paddle wheel, as the cathode rays go, they hit the paddle wheel. What does it mean? The cathode rays possess kinetic energy. That's property number 2. Try property number 3. I can notice a shadow somewhere. What about a shadow? From rectilinear propagation of light, we notice that shadows form because they directly form behind the object or the obstacle. Why? The light travels in straight lines. That's from rectilinear propagation of light. So as it travels in straight lines, when it meets an obstacle, an umbra, or simply a shadow, is formed behind that particular obstacle. So basically we find that cathode rays, similarly to light, travel in straight lines. Now let's try this one. Take a closer look. I have noticed something. Believe you can also notice the same thing. Believe what you have basically noticed is that the cathode rays have been attracted towards the anode, and specifically towards the top side. Why the top side? There is a pair of deflecting surfaces here, whereby the top part is negative, the bottom part is positive. Now notice the cathode is negatively charged because of the electrons, and they are displaced with these particular display devices, these displacement devices. We are going to look at them in the next tutorial, in which we are going to be looking at a CRO and explain why we have these two plates here. So it's deflected towards the positive side of the anode, basically because they are negatively charged. Now what we have been able to deduce is, number one, the cathode rays cause certain substances to glow. In most cases it shows greenish fluorescence or a glow. Number two, they possess kinetic energy. 3, they travel in straight lines. 4, they are negatively charged. And finally, they produce X-rays when suddenly stopped by a metal target. Now I would like you to check how X-rays are produced. You'll notice that X-rays are produced when they are suddenly stopped by a metal object. That's when you have fast moving electrons and they are suddenly stopped by a metal object. So notice the stopping is due to the anode. So if it hits the anode, for example, in the first case, when you are looking at the simple CRT, or the cathode ray tube, when it hits the anode, it will cause X-rays, or when it hits any metal target, it will cause X-rays. So that's basically what we have. So we'll be able to stop there for this particular session. Success in your preparation, and may God bless you abundantly.